Everybody, in this set of videos, we're going to introduce the idea of a vector. So vector quantities, or vectors for short, involve both magnitude and direction. If we say scalar quantities or scalars, those just involve magnitude and no direction. So here's what a vector looks like. A vector is basically a directed line segment. So here's the line segment. You can see there's an initial point and a terminal or ending point. So you have a segment there, and then it's directed because it has direction. You have an arrow showing which way the segment is, I guess, moving in a way or pointing. The magnitude of it is the length from P to Q. So the magnitude is just its length or its distance from P to Q. And we denote that like this. So we use two vertical lines on each side. And then we use PQ with a little arrow over it to represent that directed line segment. Okay, so we're going from points P to Q, and again, we show we have direction there. And then when we add these two vertical lines, that refers to the magnitude of it. Now, this is the same idea as a vector. So a vector is just a directed line segment. In your text, you will typically see bold letters in a textbook. So they may just say vector V and just bold the V. Or they could use notation like this. When I'm writing it, we typically put that little arrow above it because I can't bold when I'm writing. So you'll notice that when I'm writing, I'm going to try to use those arrows up above just to remind us that we're looking at vectors. But when you're reading in your text, you're reading online, they often won't do that. They will just bold it, and that also means vector. So you just want to be careful there. The vertical line notation, that double vertical line notation, still means magnitude, whether they use the arrow notation on the inside or if they just bold it, that's fine too. So it means the same thing for magnitude. Vectors are equal if they have the same magnitude and also direction. So for me, I would write it like this because I'm writing it by hand. So I'm going to show that those two are vectors by putting that little arrow above. In your textbook, it will just say V equals W, and those two letters will be bolded. So you just want to be really careful with the difference in notation here as you're versus reading and taking notes or writing, workout and things like that. I always laugh, well, maybe I should say always laugh here, but I have small children at home, and the Minion Despicable Me movies are ones that we watch. And there's one of them, I think it's this, don't quote me, is it the first one? I don't remember anymore, there's so many, where there's another villain named Vector, and there's actually a scene where he says his name is Vector because he has both direction and magnitude. So it's just kind of a funny way. If you forget, I don't know, I always think of that movie and I think of him saying that he has direction and he has magnitude, meaning, whatever evil scheme he's up to is going to be big. So that's your vector, if that helps you to remember it. Or next time you watch those movies, it'll probably pop into your head and hopefully you'll think of math class. So to show two vectors are equal, we actually have to do a little bit of work. So yes, we can look at pictures, for instance, something like this, right? So maybe this is one vector, and maybe this is another vector. So just looking at these, they look pretty similar, right? They seem to be going the same direction. They seem to be the same length, same distance there from the 2 points. I guess I should put my endpoints in here, right? And oops, oh, I think Griffey's gonna come say hi. Endpoint here and here at the end of those. But obviously that's not great. I mean, it's a good start to say, yeah, they look like they have the same direction and magnitude, but we do really need to check algebraically. Obviously, if the lines or the vectors look totally different, then you know that they're not equal, right? So if one of them is going like as much bigger than the other, or they're going in different directions, then it's pretty clear that they are not the same. But if they do look like they could be the same, now we're going to go ahead and bring in that algebra, and that's what I'm going to show you next. Okay, Griffin's visit is over. So as I was saying, to show that two vectors are actually equal, we have to show they have the same magnitude and direction. So the first thing to do is to look at them visually if you have the image, right? If you have a picture. So these two look like they should be equal, right? They look like they're going in the same direction, and they look like they're the same length. So they have the same magnitude. if something looks completely different, right? So something that would definitely not be equal, you know, one of your vectors maybe looks like this, and then the other vector looks like this, right? Obviously those look like the same direction, but they have two different magnitudes, for instance, right? So something like that would not be equal in that case. Or as another example, you know, maybe they look like they have the same magnitude, but they're going in different directions, right? So those also would not be equal. So visual is a great first place to start, but it's not enough. We do want to actually check that. It's sort of like we do with parallel and perpendicular lines. You know, the visual is a good place to start, but we really need to check algebraically. So let's do this example here. So we're going to show the two vectors, vector v and w are equal. And I'm going to give you an image of them. So I'm just going to quickly draw this by hand. So bear with me. And I'm just going by units of 1. So my first vector, let's see, 1, 2, 3, 3, is going to start at negative 3, 3, and it's going to end at 0, 3. So this is its starting and ending points. And then we'll do the other one in blue. It's going to start at 0, 0 at the origin, and it's going to end at 3, 6. So bear in mind, I do these by hand, so they're not perfect, but they do look pretty close. So if I look at it visually, I'm saying, yeah, they look like they could be equal, right? They look to be going in the same direction, they're pointing the same way, and they look to be the same magnitude, meaning that basically the length of them is the same. It's the same distance between their initial and ending points. So let's actually check. So the first thing I'm going to show is that they have the same magnitude. And to do that, I'm going to go ahead and use my distance formula. So I'm going to find the magnitude of v first. And in case you forgot, here's the distance formula. So we're going to subtract the x values and then subtract the y values, square both, and add together. So for v, oh, I should label these. That would help, huh? That's v, and this is w. So v will be in pink. So for my x values there, I'm looking at negative 3 and then also 0. And then for my y values, I'm looking at negative 3 and 3. So negative 3 squared is going to be 9, and negative 6 squared is 36. So this is the square root of 45. Now, there's no reason to really simplify too much here because I'm just making sure that they're the same. If I wanted a nice formal answer for the magnitude of v, then again, you could simplify as much as possible. So this actually does simplify to 3 root 5, you know, if you need a nice final answer. Now I'm going to do the magnitude of w. I'm going to use the same formula. So I'm going to subtract my x's first. So here I have a 0 and a 3. And then I subtract my y's. So this is the point 0, 0. So my y is 0 here. And then I have 6. So I have negative 3 squared plus negative 6 squared, which is going to be the square root of 9 plus 36. And you can see here that you have the same exact answer. So the magnitudes are the same, right? Same distance in each case between those initial and terminal points. So your magnitudes are the same. That's what your magnitude is. Now, the second thing I have to actually check that they have the same direction. And the way we can do that is we can use slope. see if I can keep this all on the same screen. All right, so let's do the first vector. I'm just going to label just so it helps me keep things straight. So for v, my m, we're going to use y2 minus y1 over x2 minus x1. So going up here, my y values are 3 and -3. And then my x's are 0 and -3. This becomes 6 over 3, which is 2. And then I'm going to go ahead and do my other one. So my other vector is w. And again, I'm just using the same formula. My y values in that case are 6 and 0. And then my x values are 3 and 0. So I have 6 minus 0 over 3 minus 0, which is also 2. So they both have the same direction as well. And then we're done. So, you know, v is actually equal to w. Vector v is equal to vector w. But we do have to check those two things. So again, start visually. And, you know, if it doesn't make any sense at all, like going in totally different directions, or clearly one is much longer than the other, then it's probably pretty easy to say that they are not the same. But if they look like they could be the same, now we got to do the algebra and we have to actually check. Okay. One other thing I want to talk about in this video before we go on to another video, just so they don't get too long, is just talking about scalar multiplication as well. So a couple things to note here is that if we multiply a vector by any positive real number, obviously except 1, because that wouldn't change anything. It changes the magnitude, but not the direction. Of the vector. So if we use, and I'll show some examples too, if we use some scalar multiplication, just multiply the vector by a real number that's not 1, a positive real number, then you do make it, you know, longer. So the magnitude does change. I should say it may not be longer. If you multiply by a fraction, that could make it shorter, but it changes the magnitude, but not the direction. Say multiplying a vector by a negative. Will reverse its direction. So if I multiply by negative, it's going to reverse the direction of the vector in that case. And the multiplication of a real number, we'll call it k, and a vector e is called scalar multiplication. And I guess when I write the word vector, I don't really need the line on top, so I should clarify that. I'm just being a little redundant there. All right, it's called scalar multiplication. All right, so let's go a little bit more deeper into scalar multiplication here. Kind of a lot of definitions that I'm giving you guys here. So about scalar multiplication. So our formal definition here, if k is a real number and v is a vector, then kv is called scalar multiplication. Remember too that if you're reading your text that v will just be in bold, so it won't have the little arrow above it. But where I can't bold, then I do have to put that arrow in. The vector kv has magnitude of the absolute value of k times the original magnitude of v. So whatever that k is, you take the absolute value and multiply it by the original magnitude, and that will give you the new magnitude. And the vector kv has direction, and it's going to be one of two things. So it's going to be the same direction as the original vector if k is greater than 0, and the opposite direction of the original vector if k is less than 0. Okay, so that's how scalar multiplication can affect things as we're going